Thank you. Yes, so as just been said, we're going to be talking about what every coder should know about how CPUs work, which to me is an absolutely fascinating topic. Hopefully you'll find it too. What I'd like you to get out of this is, first and foremost, like an overview of what a modern CPU can do and is doing for you under the hood. And by modern CPU, I mean anything that's been made in the last 15 years, both x86 and ARM and RISC-V even. But my experience is mostly in x86, so a lot of this will have a sort of flavor of x86 about it. I also want to tell you a little bit about how compilers take advantage of the knowledge that they have about how CPUs work in order to get the best out of the CPU for you. So most of the time, you don't have to worry about this kind of stuff, which is kind of cool. And then when you do need to worry about it, I'm going to show you some tools that can help you understand where the performance issues may be in your code or what on earth is going on inside your CPU in the first place. So first and foremost, I'm going to explain a sort of simplified, and it looks more complicated, I know, but a simplified view of what a modern CPU pipeline looks like. So first and foremost, it is a pipeline. It's a production line. Things get put on one end of the production line and they slowly make their way along. And as they go along the pipeline, different things happen to those instructions that are being fetched. And we'll talk about how that all works in a second. And then sort of in modern CPUs, something cool happens. So if you've done your MIPS style fetch, decode, execute, retire for a 4-stage pipeline from like university days and that kind of things, nothing works that way anymore. We have this front end that is in order. So anything that's in blue means it happens in order. That means each instruction is processed one after another in the order that you wrote them. And then there's this cool green stage here, which is out of order. And what does that mean? It means that the CPU is going to do some dependency tracking between the various instructions that you've given it, and it's going to execute the instructions in an order where their dependencies are satisfied, but it's not necessarily the order that you even gave them to the CPU in. Why would you want to do that? Well, most of the time, your program is waiting for things like memory accesses or complicated things like multiplies, divides to happen. And if you can find work that your CPU can be doing while it's waiting for memory accesses to complete, then you can get more work done per unit time. But it is very complicated, and that can be an issue that we sometimes surfaced to us when we're looking for performance issues. So we have this in-order front end, we have this out-of-order green execution back end, and then retirement sadly happens at the end, and it happens in order, and we all retire hopefully. And that happens back in order again. So despite the fact that all these clever things are happening and maybe your instructions are actually getting executed completely out of order, they retire strictly in sequence again, which means that as a user looking from the outside in, you typically don't notice that those instructions happened out of order. You see the program complete as you wrote it. All very cool. There's a huge caveat for this, which is where Spectre and Meltdown, if you remember the furore about those issues, there's a sort of leak from this system. Unfortunately, I don't have time to talk about that, but you can talk to me about it afterwards. So I kind of lied to you. I said, there's this sort of pipeline fetch decode, and then there's that here. There's a part that happens even before the fetching starts. So we have a system that is going to try and guess what's going to happen in your program before you've even executed the first instruction. Why is this? This pipeline here, this fetch, decode, rename, and then the green stuff over here, is many stages long. There are like dozens of cycles between the point where the information about what instructions need to be run is being fetched from memory through the caches, it's being broken apart and decoded into all of the different micro operations that go into that sequence of instructions. And then by the time they've been scheduled to run, it's a bit late if we discover that there was a branch that said we should go somewhere else now. And so typically, CPUs of yesteryear would have a little bubble in the pipeline. When the branch happened and the direction of the program moved somewhere else, everything would be discarded and the program would restart, but then we have to kind of refill the pipeline again from the left-hand side with the new address of where we're going from. That's cool and all, but when there was like 2 or 3 cycles, that was maybe okay. But when there's 12 cycles, that means every time you take a branch, you're taking this big hit of re-steering this production line. And the way that I like to think of it, it's a bit like those, I don't know if you've seen the strip mining machines. There's this huge like spinning digging thing that's pulling out ore and chucking it onto a huge conveyor belt that's like, half a mile long. And then the control unit is right at the back of that, and then some person is steering it back and forwards to try and like mine the ground. It's like, if they can only see the ore that they're mining right next to them, that's like the execution unit. And then you start realizing that you're not digging up the ore that you want anymore. Oh no, I'm digging up like just dirt now, and I wanted to be getting that. I now have to steer that pipe to the new location of where the stuff that I want. But unfortunately, I have this entire pipeline of dirt that I've got to sort of like deal with that's coming down. And so what the branch predictor is going to try and do in that situation is make an intelligent guess about where the program flow is going to go before we've even seen the program, which is a pretty difficult thing to do. With no information whatsoever, that branch predictor has to make a guess. And what it's trying to guess is there a branch coming up in the sequence of instructions that are coming? If there is, where does it go to? And for those many branches which are conditional, you kind of if then go to whatever, then will it be taken this time? And if we can predict that more often than we predict it correctly more often than not, then we can actually steer that pipeline in the right direction. And every time a branch gets hit, we aren't throwing away all of the work that's on the production line. The work was actually correct. But we also have to accept that sometimes we get it wrong, in which case, yes, we still need to throw some of that work away. But if we don't get it wrong too often, that's not such a big deal. I will talk about how that branch prediction works in a second. So having guessed where the program is going to go, we're going to start the front end. The front end is responsible for picking up data, bytes from memory, and loading them through the cache in big chunks, decoding those chunks into the actual instructions that are inside those bytes. This is where, for things like ARM processors, the encoding of ARM instructions is very straightforward. It's either 2 bytes long or 4 bytes long, depending on which mode it's in. And that makes it very straightforward to do this decode stage. But if you've ever looked at x86 machine code and the assembly code that goes with it, a single x86 instruction can be anywhere between 1 byte and 15 bytes long. And so there's a lot of complicated stuff that goes into decoding that and turning it into some kind of understandable, what is this instruction? Is it an add? Is it a subtract? Is it a multiply? Those kinds of things. And another cool thing that happens in the front end is that a process called register renaming happens, where some internal space on the chip is used to store intermediate results. And it's as if you have now like a couple of hundred registers. So most CPUs only have a dozen registers, 16 or 32 registers, and so you can often, if you keep reusing the same register over and over again, load something into A, store it over here, load something else into A, store it over here, then there's no opportunity to have those two operations run in parallel because they both want to use the A register. But we know as programmers that they're sort of two different uses of the A register. And the renamer is able to do this. So it would rewrite that into load into temporary register 0, and then store temporary register 0 over here, and then load into temporary register 1 and store over there. And so there's a lot of tracking that goes on, some clever things that go on to avoid these data hazards. So finally, we get to the point where we're actually doing some work. We have inside this execution unit, the ROB there is reorder buffer. So there's a reorder buffer which stores all these internal results while they're being assembled in the order that they're going to be completed in. And then the execution units, there are many, many of those. So we're talking about a single CPU here, a single core on a die, but it can have multiple multipliers, it can have multiple adders, it can have multiple floating point units, arithmetic units, address generators, all these things here. And what the execution stage is doing is looking for instructions whose inputs are now known and then scheduling them to run on a particular part of the chip. So if this is a multiply and we know its inputs, we can start running the multiply. That may not be the next instruction that flowed through the pipeline because we're tracking whether or not it's ready to go or not. What that means is that there are multiple units that can be running in parallel. So if we have 2 multipliers, we can be doing 2 multipliers at once. If we have several ALU units, we can be doing add, subtract, shifts and things like that at the same time. And typically, even this relatively old laptop that I'm on here can be executing anywhere between 5 and 8 instructions every single clock cycle in this execute block, provided those parts don't use the same areas of the chip. And that's where some of the some of the performance of modern CPUs is coming from these days. You may have noticed that the clock speed hasn't been going up over the last few years. We've been sort of stuck at anywhere between 2 and 4 gigahertz pretty much these days. we might have more cores on our chip so we can get multiple threads going, but even single core performance is going up. And part of it is because of the clever tricks that can be pulled out inside of this stage. Finally, at the very end of the pipeline, we retire the instructions that have completed. This is kind of like committing, finally, the instruction to having actually happened. And that, again, happens in strict program order, which means that we don't see any kind of weird side effects of having done things in the wrong order or in a different order inside of the chip. And this is where exceptions are handled. So if this is where you potentially hit some area of memory that was flagged as being not mapped and you get a seg fault, the instruction will be tagged, and when the instruction finally completes at the retirement stage, that's where the chip actually goes, okay, now we need to do something different. We need to go to the crash handlers. Similarly, this is where the fact that we've been pulling instructions that we don't know if they're the right instructions. You know, this branch prediction system is happening. We're following along the thread of where we are just making a guess. And if we make a mistake, we need to be able to throw away the work that we were doing. And the way that we throw that away is by just not retiring those instructions when we discover a branch that went wrong. So having executed a branch, we check it against whether or not we predicted it would be taken or not. And if it was right, no harm, no foul. If it was wrong, all of the instructions that happen immediately after that branch need to be thrown away. And the way that we do that is to just discard them from the retirement buffer and make sure they never retire. So there's a lot of clever tricks going on in there. That is a super, super high level view. And there aren't even half as many, as I say, these are like anywhere between 12 and a couple of hundred of cycles before a single instruction makes it from one end of the pipeline to the other. But hopefully it gives you a sort of grounding. And now we're going to talk a little bit about some specifics, and I'm going to give you some tooling to show how it happens or how you can measure it yourself. So this is more confusing a picture than I wanted it to be, unfortunately. I have another presentation where I go into a deep dive in how the branch predictor works. And I stole some slides from it, and now I'm like thinking, oh gosh, this is probably more confusing. But the general gist of the branch predictor is that it has a little lookup table, and every time the execution system discovers that there's a branch, and it took a branch, it sends a message back to the branch predictor saying, hey, at address 1000, there's a branch to address 2000. It goes, okay, and it notes it down in a table. That table is the branch target buffer, and you can think of it like a hash map. It's a hash map that gets replaced over time. There's only a certain number of entries that are in it, so we've only got a couple of hundred of those, whatever. And that means that the next time we see that address, we will predict that we'll go to address 2000 rather than just following a linear line of one instruction after another. That's great for unconditional branches, but many branches are either conditional or have a derived destination. They are like a switch statement or a virtual function call in C++ terms, where we don't actually know the destination. I haven't even put that on here, but the most common case we think about with branch prediction is whether it's taken or not. And so the ways that this is done is a sort of relatively closely guarded secret by each of the vendors, because the key to great performance is accurate branch prediction. And AMD and Intel and ARM don't really publish many details about how these branch predictors work, but they have luckily been reverse engineered by some smart people. And broadly, what happens is the instruction address where a branch is known to be, plus some amount of history, both locally for that specific branch and globally for all branches. They're sort of hashed together to give a unique sort of fingerprint for when I'm at this branch and I have seen branches that go taken, not taken, 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 not taken, something like that, then go to slot 7 in these predictors over here. That's like where the hash lands. And then in that predictor table, I just keep account of whether or not it was taken or not. And I have a 2-bit counter. Every time it's taken, I add 1 to that. And every time it's not taken, I subtract 1 from it. And then I just use whether or not it was taken before or not as the prediction for whether it's taken this time. And it works remarkably well. And there's a lot more subtlety to it. There's some agreement predictors. There are multi-levels of this kind of stuff. But broadly speaking, it's kind of a hash lookup and a bit of history keeping track of what happened last time. Is it important, though? I mean, I've been waxing lyrical up here about how important it is. I'd like to show that the branch predictor is actually valuable even when you're writing something in Python. So I've got a bit of Python up here, and this Python code is just summing over a list of integers. The list of integers is a big set of numbers between 0 and 255, And essentially in the middle of this loop here, this is terrible Python code, don't write Python code this way for this kind of thing. But we're saying, keep track of a total sum of all the integers, and then separately I want to just keep track of the sum of all the integers that are less than 128. Seem reasonable so far? So hiding in there is a branch. It's not a specific branch in like some object code, some assembly code, but deep inside the Python interpreter, we know that there's going to be some kind of switch on the Python bytecode, and there's going to be a pattern in the ways that it's going to be jumping around. And I'm hoping to show that the branch predictor can be affected by whether this branch is taken or not, and measure it. So what my approach is going to be is I'm going to run this piece of code with 10 million random numbers, again between 0 and 255, and then I'm going to run it again with the same data, except I sort the data first. Now this is a kind of very counterintuitive thing to do because it's the same numbers, right? I'm not pulling any tricks here. Sorting it doesn't do anything clever like bring it into the memory caches or anything like that. I've done versions of this where I write the file out and just have two copies of the same data, one where the file is sorted, one where the file is not sorted, and I run it over those. And it gets the same answers. So if we run it for 10 million items, this is surprisingly quick really for Python, 0.7 seconds it takes to run over the unsorted data. Now, again, I've been leading up to this point here. This is sort of a leading question. Do we think it's going to go faster or slower if I give it sorted data versus unsorted data? Faster. People think it's going to be faster, and they're absolutely right. It is measurably faster, even in Python, an interpreted language running over 10 million numbers, if the numbers are sorted first. And if we just take a moment to think about that, the hypothesis would be that, we'll go back to my code, 1 second, that this branch is essentially unpredictable if I give it random data. It is equally likely for the number that I'm going in this particular iteration around the loop is greater than 128 or less than 128, right? Equally likely, it's a coin toss. And so there's no pattern at all for the branch predictor to latch onto there. It will make a prediction and it will be wrong half the time, and then I'll have to undo this work and re-steer the pipeline and start again, all that kind of good stuff. But when the data is sorted, this branch is jumped over. For the first half of the file, all of the values are less than 128 because we've sorted it. And so this if statement will be taken, i.e. the branch won't be taken. And then as soon as we get to the midpoint of the file, we'll discover the first value that's 128 or greater. The branch predictor will probably mispredict that, but quickly it will learn that this branch is now always taken. And so what we've got is a predictable branch in the case of the data being sorted. But is it really that? This is a relatively small change of 0.08 seconds, 80 milliseconds difference there. Is it really the branch predictor, or have I just done something silly in my tests? It's a good question. It's one I always should ask yourself. Whenever you're doing performance-related stuff, you have to measure things over and over again and really try and look for some of the more esoteric hypotheses. So this is a tool that I use. So most of the stuff I'm going to be talking about is Linux-based, but there are equivalents for Windows. vTune, for example, is Intel's sort of GUI-based version of this that is available both for Windows and Linux. Perf is a tool that uses the counters inside the chip. So the chip itself keeps track of interesting events that happen. And you can configure up to between 4 and 6 counters and measure one of thousands of different things that can happen on the chip. This is like telemetry inside the CPU. And so what I've asked it to do is use 2 of the counters to count both the number of branches that we encountered and the number of branches that we missed. And as you can see, when I'm running my Python code here, with the data being unsorted, i.e. random, then there are 20 billion branches and 124 million of them were misses. This is pretty incredible, right? Remember, this is random. Remember also that there's tons of other branches in the Python interpreter, right? But 99.4% of branches have been correctly predicted. Amazing. If we run it with the sorted case, though, we see that we drop somewhere in the region of 50 million mispredictions, and we go down to 0.37 branches are being mispredicted. That's amazing, absolutely amazing. So I think it's clear that we could say that, like, and if you measure some of the other performance characteristics of the CPU, it's pretty clear that the only thing that can explain the speed up really is this branch misprediction. Another thing that Perf can do is it can show you the instructions that actually generated the mispredictions, and you can draw some conclusions from that and sort of work backwards and sort of say, no, it really is this particular bit of the code. So that's pretty cool. But you know, Python's a bit of a weird language to demonstrate microarchitectural effects in, so let's try C++. So this is the same code written in C++, exactly the same kind of flavor to it, just, you know, slightly different syntax. And the unsorted takes 7.6 milliseconds. Is the sorted going to be faster or slower? And you know this is going to be a trick question, don't you? Anyone hazard a guess? No one's going to put their neck out on the line. The sorted case, if my clicker works, exactly the same. So somehow C++ can teach the branch predictor to predict random events, maybe? I don't know. So what happened here? So well, first of all, let's throw perf at this and see what happens. So if I run my branch prediction code, the C code version of this, you can see far fewer actual branches were taken because, you know, now we haven't got the Python interpreter that's being actually run. We're just seeing that tiny loop of code that's doing the if check. 38 million branches are missed when it's unsorted. And when we sort the data, exactly the same, within the noise of the perf system itself. So perf, unfortunately, is not a perfect system. It's got a certain amount of noise with it. So how come we're able to predict these branches? Well, let's go and have a look at the code. So one thing we can do, I hope this works, fingers crossed. Drum roll, there we go. So this, oh my God, that's so bright and white. In a second, it'll go into dark mode. And you can see, unfortunately, that I didn't try this on the actual resolution that we were in here. So what I've got, this is Compiler Explorer, which is a website that lets you put in your code on the left-hand side, and then it shows you the assembly code equivalent on the right-hand side, and then you can mouse around inside of here. If I can scroll around somewhere. And as I'm scrolling over the various different parts of it, unfortunately, again, because there's the zoom here, if I can zoom it out a little bit. There you are, that's a little bit better. Okay. So as I'm sort of mousing over, you can see that I'm highlighting the instructions that correspond to those particular parts of the code. And it's a valuable tool in terms of working these kinds of things out, but because it's easier to look at the code on a big screen here rather than me trying to fart around with the website, I've pasted it into here and I've put the comments about what's going on inside the code here. So this tiny loop here is this loop above. The first part we're doing, and I'm assuming, you know, like it's been a while since most of you have looked at assembly code, I'm sure. But anyway, so we're reading the next value into ECX, it's a register, don't worry about it, and then we're just adding it to R8D. R8D just happens to be the register that it chose to put total sum in. So that is the first sort of line there, total sum plus equals integer. This second part here is cleverer. What the compiler has decided to do is work out unconditionally what the value of sum below 128 would be, regardless of the value of integer. It's just going to add integer to it anyway. And then it does the comparison, and then it uses a conditional move that says, if the comparison was below, that's what the B of CMOV B is, if the comparison was below, then move this temporary value back into the sum below 128. Otherwise, leave it alone. And so it's kind of a hardware ternary operator, you know, like the question mark. And the important thing about that is that there is no branch here. There's nothing to predict. There's nothing to mispredict critically. The compiler has decided to use this conditional loop here, conditional move here, and then there's some other nonsense here. So there's exactly one branch, this JNE at the bottom here, exactly one branch in the whole program, and this is very, very predictable because it's going to be taken 10 million times, and then the last time around the loop it's not going to be taken, and the predictor will get it wrong then, but I think by then we've got the benefit of the branch predictor out of it. So the compiler is pretty smart here. The compiler has taken a bet that doing the add unconditionally, even though it's inside an if statement, is worth doing, like the performance of it is worth doing, to be able to do this conditional move. Now, if there was a side effect in there, if that if statement had like a print statement or something like that, obviously the compiler couldn't run that bit of code. It knows that there's no side effects to that particular aspect. So the compiler has chosen to do this. It doesn't always make this choice, but it has in this instance here. So what if I turned the compiler's ability to make that conditional move off? So I've got a horrible hack there, which I compile it with no if conversion, which says to the compiler, don't do that. Then if we use the sorted case, we see that we've got similar results to before. There's more branches now, because now we've got two branches. We've got a branch in the middle of the code that's jumping over, but it's sorted, so it's predictable. So the actual miss rate is still 0.37%. So far, so good. When we run it on the unsorted data, 24% of all the branches are mispredicted, which is exactly what you'd expect, right? That loop has 2 branches, one of which is perfectly predictable, so half the branches will be perfectly predicted. The other half of the branches will be wrong exactly half the time, so that's where the 25% comes from. So that is monstrous, and it takes 39 milliseconds versus the 9 if we just use the branchful version versus the 7 if we use the CMOV version. So the compiler got it right here. The compiler made the right call, and you can see that branch prediction correctly is important to be able to do. This looks very artificial, I get it. I mean, it's a surprising thing that sorting your data could make your program go faster, I get. But, so is this realistic? And yes, actually, I have another presentation where I write a ray tracer, and the end of the presentation, it was meant to be about C++ style, not about performance at all, although that's my thing. By the end of it, suddenly I'm running one of the versions, and it's so much slower, and I couldn't work out why. And it turned out that there was a branch that was totally not predictable in the middle of this ray tracer, and making a single character change in my code made that branch predictable, and the thing went 3 times faster. It was brilliant. It doesn't happen very often, right? But for these kinds of things, it can do. All right, we're going to move on to, how am I doing on time? Not very well, so I'm going to have to start going a bit quicker. We're going to talk a little bit about execution. I originally had some very morbid picture here, and then I thought I'd probably come up with something slightly better than that for this. So I'm going to try and explain with a little sort of real-world worked scenario of something which hopefully people have been are familiar with, which is a Bloom filter. If anyone know what a Bloom filter is? A few nods in the audience, yes. So super quickly, a Bloom filter is an acceleration structure, a probabilistic acceleration structure, where you can ask the question, is my value W in this set or not? And the answer it gives back is maybe and definitely not. And why the heck is that useful? Well, that set is actually quite small. The maybe, obviously you have to be able to deal with false positives. It's useful for things like databases where maybe if you definitely know something's not in the database, there's no point going to load the B tree off of the spinning Rust disk or make the network call over to the far end. So you can use it for local acceleration. But sometimes you're wrong. So the way that it works is we take our inputs, which are either X, Y, and Z in this instance, and we hash them with different hash algorithms, or with some perturbation of hash algorithms, and we set a 1 bit in all of the locations in an array of values where those hashes land. And then to ask the question, is W in this set, we do the same thing, and we ask, are there 1s in all of the locations? So obviously there's going to be some times where these things collide, and that's where we get the maybe it is and when it isn't. But if it's not in there, then at least one of those bits won't be set. And that means it's definitely not in there. We never set any of its bits. So really the code looks something like this. We have this sort of, is it present? I'm just using ID here. We do some kind of looping over how many times we're going to hash our value and get different hash results. And we check the bit and we count, and if the count is equal to the number of hashes that we chose, so I'm picking 4, there were 3 on the example that we just saw in the picture. If it's 4, it might be in there, and if it's less than 4, we definitely know it's not in there. And this scramble function, I've just used like murmur3 to do like a hash, a very crappy hash, frankly. And then given the hash value, we need to be able to sort of say, well, which slot in my table do I need to check? And I'm going to just use a modulus, so I'm just going to use the size of the table, and I'm going to modulus with it. And as you know, all good folks who use hash tables know we should pick a prime number size for that table so that we get the least number of aliasing and the horrible problems with coprimes. And I'm going to show very quickly something that we can do here. So I'm going to go back over to Compiler Explorer, which is going to be very difficult to see in this scale. So again, there's a chunk of code in here. This stuff on the left-hand side is the murmur hash thing, so it's a bunch of multiplies and shifts. And we're looking at this L2 loop here, which is the loop over the 4 times that I'm looking inside the table. And what I can do is I can select an area of code, and then I can paste it into an analysis mode inside Compiler Explorer. But because that involves a whole bunch of fiddly things, I have a canned link that was going to take me there. So you'll have to trust me that this can be done reasonably easily. So what this is doing is using something called LLVM MCA, which is a lot harder to say than you think when you're on stage, which is the machine code analyzer. It is part of LLVM, which is part of the Clang project. This is the compiler. And it uses the same knowledge that the compiler uses about how long instructions take and which things depend on what to do the scheduling inside the compiler. It allows us to turn that on its head and say, given an arbitrary bit of code, what would the CPU do? And so what this is predicted is that this would take 4 iterations of the code on the right and left-hand side would take 148 cycles. And the cool thing about this is, if I can maximize it, sorry, this is a tiny little thing here, there is a little view down the bottom here where this is a sort of timeline view. Far off on the right-hand side are the instructions. So going from the top to bottom is the program running, each of those instructions. And on the left-hand side is kind of a visualization of the pipeline that we've been talking about. It doesn't have all the fetch and decode part, it just has a single D for decode. But each column is a unit of time moving from left to right. So what it says is in the simulation, in the first clock cycle, 0 here, all of these instructions were decoded at once. So it can decode multiple instructions at once, which is super cool. I don't think it can actually decode this many, but we're going to go with the tool. On the second cycle, that is the 1 column here, 2 of the instructions started executing. That's what that lowercase e is. And these ones with the equals were blocked. They couldn't start executing because they depended on some of the values from the earlier instructions. But also, meanwhile, we've decoded the next set of instructions, and so on and so forth. Now, I'm not going to go over it in huge details, but the equals usually is a bad sign. That shows that there's a dependency. It's not able to run those instructions that it otherwise would. And probably you've noticed that there's something horrible coming down the pipeline here, quite literally. This instruction here with all the E, which is the correct sound to make when you see this. This is the divide. You're like, I didn't see a divide in that code. But the modulus operation that we were doing, the only way to do a modulus is to do a division and get the remainder, which is what the div instruction does. And in anything but the very latest version of Intel processors, at least, these 64-bit divides can take anywhere between 80 and 100 cycles. I don't think this is actually right. So that's pretty bad. But while we're here and looking at this sort of view here, this is sort of underlying the sort of the sort of how the pipeline works. Despite clearly the 2 instructions immediately after the divide here with all the equals is, those are dependent on the result of that divide. They're blocked, hence they're just waiting and waiting for it to complete. But the next iteration of the loop, which the branch predictor has already sort of sent us around, even though we haven't executed the branch yet, right? It is predicted and it started running the next part. And so all these instructions here are actually from the next iteration of the loop. So we're getting this cool out of order aspect that I described earlier. And then obviously the big dashes and the R is them retiring at the very end there. So they're all having to retire in sequence. And so I can kind of follow it down and follow it down and follow it down. And what we see is that, yes, it takes absolutely ages to get an answer out of that. Excuse me. So what could you do about that? I mean, maybe you're stuck with it, right? But this is a probabilistic data structure. If we can trade off a tiny bit of the performance of the hash table that's sort of underpinning it with by saying, let's not use a prime number size anymore. Let's use a power of 2 size of that table, and we'll encode that by saying, I'm going to only allow my table to be constructed with the log 2, not power 2, the log 2 size of the table, and then I'm going to construct it with 1 up that size. So, like, let's have 65,000 entries in my table. Now I know that my bucket operation doesn't have to be a modulus with an unknown number. It can be an AND with the filter size -1. And if we look at that code, never do things that rely on the Wi-Fi, we can see that this thing now takes 33 cycles. And this is a much healthier, if my mouse would work, click, 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 much healthier timeline view down here. This is what I would expect instructions to look like. Everything is kind of just taking a small amount of time and is retiring pretty soon afterwards. It's not waiting for huge amounts of time. I mean, there are still waits happening in here, and we're still getting some benefit of doing more hashes there. But it takes substantially less time. And this is one of those things where I think we forget that computers are incredibly, incredibly fast, but divides are still really, really slow. Now, that is actually not true in the most recent generation of Intel machines. They've now got them down to tens of cycles. But those divides are expensive, and they're not pipelined, which means that you can only do 1 divide at a time on 1 CPU. And when that completes, then the next divide can start. Unlike multiplies and adds and things like that, which may take multiple cycles, but you can start one every single clock cycle. So divide's bad. If you can avoid them, fantastico. So that's 30 cycles versus the 148 that we saw in the first instance there. Now, we've been using a simulator here. This is where I have to say a token exhortation to always benchmark your code with real-world performance rather than relying on simulations, but I wanted to show it as it's an interesting way of looking and visualizing about what's going on inside the CPU. Can the compiler save us? Yes, he says with a catch in his voice. If the compiler knows the modulus value ahead of time, if it's not just a value that we sort of call dot size on something and get a dynamic answer back, then the compiler can do a trick where it effectively turns that modulus, which is a division, into a bunch of multiplies and shifts. And you're like, how can we make a divide out of multiplies? I mean, for integers especially. Well, I mean, the way that I would do this is you take the reciprocal and multiply by the reciprocal, right? That's a way of turning a divide into a multiply. And this is exactly what the compiler is doing here. The compiler has got this horrible constant up here is essentially 1 over 1021 in some kind of fixed point representation. And then it does a whole bunch of multiplies, and then it shifts the result back down to get the answer of the division. And then it has to do some other nonsense afterwards. And the compiler can prove to itself, there's an algorithm inside the compiler for determining the minimum number of instructions to generate the modulus for any value. And one of the cool things about Compiler Explorer is that we can actually edit this, and we can sort of like say, well, if it was 15, how would that look? And the compiler can generate even better code. If it's divide by 3 there or whatever. Again, we sort of see that it has all these tricks up its sleeve. It knows how to do this for it, but it does rely on it knowing ahead of time, at compile time, what your modulus is seeing, if that's a word, with. So there are some hash implementations that use some tricks to have a jump table to jump to one of the n moduluses that they have, that they support. There's also a library called libdivide, which lets you like JIT compile divides if you have like a configuration file that you load at startup, and then you can JIT yourself a divide by the value in the configuration file. And then you get the benefit of the compiled version, but you can still have some dynamism. Okay, in the very few moments that I'm starting to run short on, I can't really talk about performance without talking about memory. As you're all aware, memory is like one of the slowest things that you can have in a computer, give or take the divide I've just talked about. It takes anywhere between 80 and 100 odd nanoseconds to access the main memory in your computer, the many gigabytes of memory. And there are these layers of caches that try and hide that away from us. We've got 1 nanosecond time for L1, but it's 32K. My first computer had 32K in it. Now it's just a cache. It's kind of sad. 256K for L2. These are representative, the order of magnitude-y field, because every computer has a slightly different setup of these things here. So the way that I'm going to expose this is with the torture test for memory, which is to have a follow the linked list piece of code. So we have a linked list, we have a pointer to the next one, we have some data, and I'm going to sum up all the data by following the linked list's next pointers. And I'm apologizing, I'm going to go quick here because of time constraints. So yeah, it's pretty much straightforward, follow the linked list. I have 10 million elements, which is 150 megabytes worth of data. If I just treat it like an array, that is, I allocate them all one after another, and I ignore the next pointer, and I just add the data of them one after another, which is disingenuous, but this gives us our lowest sort of, the fastest it could go, then it takes 11 milliseconds to churn through 10 million elements. For a linked list, it takes 24 milliseconds, which is not all that bad. It's only 2.12 times slower. Now, everyone loves to hate on linked lists, so surely they're fine, right? I cheated. In that particular example, what I did is I pointed the linked list entry at the next element in the array. So it was really just following an array, just in a more complicated way. Now, what that's showing is that data dependencies from one iteration to the loop is what's causing this slowdown. This is not memory access times, because it's the same amount of memory in the same order that we're reading one after another as it is in the array element. It's just that the prediction system can't follow along and start executing the next element of the loop ahead of time, because in an array case, it's just you've just added 10 to it to get to the next one, 16 to it to get to the next one. In the linked list case, you have to wait for the pointer to be read in from memory to follow it. It doesn't know that it's going to land in the next bucket, right? But something does do, actually. Interestingly, the L1, the L2, and the L3 caches all have predictors built into them, and what they look for is patterns of misses. And if they see the same instruction causing a miss in the cache over and over again, they predict how far that instruction is striding, if it was a strided memory access. And then they start prefetching ahead of time from L1 will prefetch from L2, which will prefetch from L3, which will start prefetching from memory. So this is actually why this is so fast. If it wasn't prefetching ahead of time, then every 64 bytes, we'd slam into a miss, and we'd have to wait for the whole time for the memory to be pulled in from real RAM. So it's pretty clever. So this is what real results look like if I actually randomize the pointers and make it jump all over the shop inside memory. Now we're exposed to the true cost of that memory. So now it takes us 1.3 seconds to get through our data. And again, I want to prove to you that that isn't just because I made a programming mistake. This is because of the memory system. And another thing we can use here is this approach to a performance analysis. It's called top-down analysis, where there is a sort of set of a set of different counters inside the CPU that are grouped together as being either front end, back end, or whatever, and there's a sort of little chain, and it will keep running the program over and over again, changing which counters it's looking at to try and drill down into what is the actual cause of the performance issue. And so the top level analysis is, are the instructions just retiring, which means that there's nothing you can do about it, the CPU is going through them just to have fewer instructions? Is it because you're speculating badly? Is the branch predictor the problem? Are you back-end bound, i.e. is there something in the execution system? Or are you front-end bound, which we haven't really talked about, but that whole feeding system of reading bytes from memory and decoding them can itself be a bottleneck at some stages. So if we run it on our, if we run it on, on our code, we can see that of those top 4 categories, we're definitely back-end bound, which is not too surprising. That's where the memory accesses are going to happen in the back end when the execution is actually happening. And we can see that for the array version, we're only 68% bound. For the linked list version, we're 85% bound. And then if we're doing it random, then we're essentially just totally, all the machine's doing is waiting in that stage. And we can drill down and we can give it more command line flags here. So I'm still using Perf here with different flags, which you can look at on the slides. We're definitely memory bound. There's all the other things we could be bound by. Heavy operations, light operations, so a divide would be counted as like a heavy operation, and all the adds and subtracts and things would be light operations, and then there's some fetch things, there are mispredictions. So we're memory bound, and if I then say, well, let's look at what the memory bound is, drill down into that, we're totally bound by DRAM over here. 67% of it is waiting for that last level cache, so actually going out to the real memory. So it's not that we're just like ping-ponging stuff between L2 and L3, we're actually going out to real mortal RAM. I don't understand why we're not L2 bound, incidentally. So if anyone has a theory as to why that's happening, I'd be interested in hearing about it. Anyway, in conclusion, as I'm pretty much at time, CPUs are complicated. We've been over the pipeline. I've talked a little about what out of order means. We've talked about why the branch predictor is so important, and a little bit about memories and caches. Luckily, we can rely on our compilers most of the time to do the right thing if we give them the right information critically, and I've shown you some of the tools that we can use to understand. We didn't cover tons of things. This has all been a single core on a single machine. We didn't talk about symmetric multi-threading or hyper-threading, the multiple cores and the cache coherency issues that come from that. There is also SIMD, which is where each instruction is doing multiple pieces of work at once for the same cost, which is pretty cool. And there are some other cool tools called kcachegrind and uICA that can do even more analysis and drill down on that. Thank you, everybody. Thank you very much.